So thank you everybody very much for joining today for this IRENA seminar. I am very pleased to be introducing to you all Alex Kemp. Alex got his PhD recently in 2022 on the population synthesis of novae at Monash University. And he's recently started a postdoctoral position in Leuven in Belgium, where he's working at the intersection between binary stellar evolution and astroseismology. So this is the larger scale end of the IRENA network's areas of expertise. And I'm very excited to have him present today his talk on the viability of novae as sources of galactic lithium. So Alex, when you're ready, if you'd like to take it away.
Sure, and thanks for the intro, Rob. Hi everyone. So today, as Rob said, I'm going to be talking to you all about novae in the context of galactic chemical evolution. So first I'm going to be giving a bit of context about sort of what novae are and some of the underlying processes, physics and concerns, sharing a bit of a window into novae from a population perspective, and then finally giving some context, if you will, of novae and their role in the origin of the elements, in particular lithium, as sort of hinted by the title. So without further ado, let's get into novae. Or maybe we'll just stay on the title slide. Here we go. So novae are a optical transient phenomenon that occurs on the surface of white dwarfs in binary stars. So before I get into that in more detail, I thought it would be good to have a bit of a refresher on what exactly a white dwarf is and some of their key characteristics. So in short, a white dwarf is an inert exposed stellar core that has the property of it being supported by electron degeneracy pressure, as opposed to, for example, radiation pressure or something like a more conventional star. So as our star evolves off the main sequence from the HR diagram, up the giant branch through core helium burning, and then finally off the asymptotic giant branch, once it loses its envelope, it then exposes hotter and hotter temperatures. Well, finally, you've got the remnant bare core. Once it's blown off all of the envelope and ceased and whatever minor burning remains, and then it just sort of slowly evolves down here on the HR diagram as the white dwarf cools, where it may undergo processes like crystallization, for example. So what do you need to know about white dwarfs? They are small and compact. So here is Earth. Here is a roughly 1 solar mass white dwarf, and they're about the same size. So they're small, they're compact. For a bit of context, a neutron star, the next scale down, that's about the size of a city. So they're not ultra compact objects, but they are considerably more compact than your regular star. These typically white dwarfs can be characterized also according not only their mass, but their composition, both of which are related to the evolution of the progenitor, in particular its initial mass. So these are sort of, in a very rough, approximate way, some of the different white dwarfs you might come across. So you see you've got oxygen neon white dwarfs on the more massive end. So these typically come from more massive progenitors. Carbon oxygen white dwarfs, by far more common from less massive progenitors, such as our sun, for example. That's expected to end its life in a 0.6 solar mass white dwarf. And then you get these helium-CO hybrids and helium white dwarfs. So these are actually binary phenomena. In that you require stripping, so binary stripping up on the giant branch in order to form these, but these can be very small indeed. So that's white dwarfs. What about novae? So novae are a phenomena associated with accreting white dwarfs. So an accreting white dwarf system is shown schematically on the left here. So you have your, think of it as a conventional star, perhaps a giant star, or maybe even a main sequence star. And it's accreting onto, in this case, through an accretion disk, onto a white dwarf in the middle here. So these systems are interesting for many reasons, but in particular they're interesting because of some of the things that they can do and produce. Type 1a supernovae are perhaps the most well-known and maybe even the most important example. So these output very important nuclear synthesis into the interstellar medium and also underpin our knowledge of cosmology. So accreting white dwarfs are absolutely central to our understanding of type 1a supernovae. Depending on the composition of that white dwarf, it may collapse into a neutron star, in this way contributing to binary neutron star populations from stars that otherwise perhaps wouldn't. And then finally, the main topic of this talk is that they can erupt in nova explosions. So unlike the first two, which involves in one way or another the destruction of the white dwarf, novae do not involve destroying white dwarfs, at least not intrinsically. So in a nova explosion, what happens is you accrete material onto the surface of your white dwarf, say hydrogen, could be helium, but let's say hydrogen, for example. And this material piles up in a layer, and this layer gets thicker and thicker. And as it does, the base of this layer is increasingly compressed and heated until finally the conditions for hydrogen fusion are met. And in this environment, this happens explosively. So you get explosive hydrogen burning, which carries with it unique nucleosynthetic signatures, that then lifts off the envelope through which the nucleosynthesis is also mixed into the envelope. And then that blow up of the envelope, which then is lost into the medium, is what we observe as a nova explosion. So because the white dwarf survives, a single nova system will typically undergo many, many nova explosions throughout its lifetime. So that's what a nova is. So what's my angle? What am I trying to investigate in terms of my research and so on? Well, I'm interested in how, first of all, answering the question of how well we can predict rates and distributions of hydrogen and helium novae. So a helium nova is exactly the process I just described, except we're accreting helium instead of hydrogen. So this changes the nucleosynthetic conditions for burning, of course, which changes a lot of the parameters, but otherwise you can sort of view them as similar. We have observed one helium nova in 2000. So this is V445 Puppis, the first and so far only helium nova. Anyway, back to the slide, where I'm also interested in particular the evolutionary pathways leading to this phenomenon. So in other words, how do we make these systems? What is the evolution pathway for most systems? What are their characteristics and so on? And then finally, what role do these play in the bigger picture, such as the chemical enrichment of our universe? So I mentioned type 1a supernovae are very important for things like ion group elements, but what about novae? So it's been known for a long time that their ejected mass is certainly far lower than type 1a supernovae. But what elements, right? What elements should we be looking for? So, you know, the title of the talk does have lithium in it. So yes, certainly novae are interesting in terms of their potential for producing lithium, which we have problems explaining in the sun, for example, in terms of that protosolar abundance. But also rare isotopes of carbon, nitrogen, and oxygen. So carbon-13, nitrogen-15, oxygen-17 have all been hypothesized to have a nova origin. So the way that I approach these questions is using two theoretical methods, if you like. So the first is binary population synthesis, for which I use JINA-CEE, which is developed by Rob Izzard and company at the University of Surrey. So binary population synthesis codes, all you need to really know for this talk is that they're able to rapidly evolve many, so 10 to the 5, 10 to the 7 isolated binary systems, all the way from birth, so a double main sequence binary, all the way until death. And they're able to do this very quickly, which is important because binary parameter spaces are large. So you need to be able to run these systems very quickly. And the other code that I use is Omega Plus. So Omega Plus is sort of built on top of Omega, which is a one-zone galactic chemical evolution model, which is in turn built into top of Sigma. This is not the logo. This is just the text. I couldn't find a logo, so I just put it on top of a galaxy. But what you need to know about galactic chemical evolution codes is that they're able to rapidly evolve entire galaxies, but in a spatially average sense. So what I mean is you don't see structure within this code. Instead, we essentially take one pixel, apply it over the entire galaxy, and we say, okay, on average, what are the properties? What are the effects of the stellar physics, the galactic physics, and that sort of thing? So what effects do the different assumptions we make about that have on the evolution of this galaxy and what we observe today in terms of specific elements and isotopes? They can also be used for answering questions like, okay, what are the most important stellar sources for certain isotopes? Right? How does, for example, novae, how does that compare with AGB sources for, say, carbon-13, right? They're very good at answering these kinds of questions, which happens to be exactly what I wanted to answer. So by combining these two, we have a nice holistic approach to dealing with the binary physics in a decent level of detail, but then also answering the bigger picture questions. So I'm going to talk a little bit, only briefly, about the NOVA model, but suffice to say that novae in population synthesis have typically only been really treated in an average sense. So what I mean by this is you've got your donor star and it's accreting material onto the white dwarf. So the usual way of accounting for novae is that you define an accretion efficiency parameter eta, which is simply saying that of a certain amount of mass, dm, how much ends up lost from the system due to your nova explosions on average, and how much remains on the white dwarf. So in this way, you can approximate the growth rate of your white dwarfs, and you can say, okay, how many type 1a supernovae do I want to make, for example? This is better than nothing, but it's not really good enough if you want to be looking at nova populations in detail. For example, finding out how much nova ejected in each nova explosion and the physical conditions of the binary surrounding all that. So we made a more sophisticated model, which we put into binary C, where instead of just treating novae as an average sense, we treat each nova explosion individually. So what I mean by this is we are tracking not just the mass of a white dwarf. We're now distinguishing between the carbon-oxygen or oxygen-neon core of our white dwarf. We're tracking a mass of helium, and we're tracking a mass of hydrogen, all of which we can track independently. So as material accretes, we essentially are filling up this, think of it like a metaphorical bucket, until we reach the critical ignition mass for hydrogen. So this is a function of the white dwarf mass and the accretion rate that we calculate based on fitting formulated detailed models. And once that critical ignition mass is reached, we say, okay, time to set off our nova eruption. And then we apply that accretion efficiency eta to decide how much material, which again is determined by the mass of the white dwarf and its accretion rate, is lost from the binary versus remains on the white dwarf and changes its total mass. Right. So, and the power of this is that this allows us to essentially count how many novae each system undergo, the conditions under which they go, in a relatively realistic way. So that's all I'm going to talk about our method of this talk, because I really want to focus more about some of the interesting results that we found. Feel free to obviously interrupt with questions if you like, but for now I might continue and talk about some of the characteristics of novae as a whole and some of the interesting things that came out. So this first results section is in the context of something called a simple stellar population, which just means we take a single burst of star formation at time equals 0, and then we watch our population for 15 gig years and count up all the novae. So this is not so much a realistic for applying to observations, but it's very useful for saying, okay, what physical influences are important within the our nova population, right? What physics do we expect to be important? And one that's always interesting to look at is common envelope physics, right? So a common envelope occurs when unstable mass transfer onto the accretor causes its envelope to expand very rapidly, such that you've essentially got two stars sharing an envelope. So in this environment, you typically get a significant reduction in radii or even a merger. But the main reason it's interesting here is that exactly how much of a reduction you get and the physics surrounding this are highly uncertain. So it's very useful to know whether we expect, for example, nova rates and predictions around that to be sensitive to common envelope physics, for the simple reason that we don't understand common envelope physics very well. And so we have these two plots. So these plots, there's a little bit going on here, but the main point is that you've got the total number of common envelope events, and then the common envelope events prior to first hydrogen novae. And then we distinguish between hydrogen nova systems and hydrogen nova events. So the distinction here is that we call anything a hydrogen nova system as long as it undergoes one nova explosion. Whereas here, we're weighting by, okay, if system A underwent 2 nova explosions and system B underwent 100, then system B is counts for more in this picture, right? So this is perhaps more relevant if you're interested in explaining overall nova rates, whereas this is more relevant if, for example, you were just interested in, okay, accreting white dwarf systems that produce novae. And there's two very different pictures here, right? These distributions are actually very different. If you care about nova systems, then 85% of all your nova systems never undergo a common envelope. But this 15% actually account for something like 80% of all hydrogen nova events that are produced from a population. So to answer the question, do common envelope physics matter? Yes, or at least they might, in that most of the nova events produced by any given population or burst of star formation, to put it another way, they all have 80% of them have a common envelope event prior to the first hydrogen nova. So there's certainly great potential for it to be sensitive to this physics. Okay, let's do this. Okay, I might go through this slide only briefly, but suffice to say, we can also look at a range of distributions, for example, the recurrence times. So this is worth briefly mentioning because it highlights an idea that I'm going to come back to when it comes to the nuclear synthesis of novae. And that is that different white dwarf masses have very different critical ignition masses. And this is important, or I should say illustrated here when you look at the recurrence times. So more massive white dwarfs, because they're much higher surface gravity, they are much better at compressing that hydrogen layer, and therefore they get the novae occurring with less material accreted. So what this manifests as if, for example, you've got a constant accretion rate, then you get much lower recurrence time, so time between successive nova eruptions in these more massive oxygen neon white dwarfs than you do in the lower mass carbon oxygen white dwarfs, right? There's also trends in terms of the donor type as well. So that, for example, evolved donors also are favored in terms of these recurrent nova systems, so the ones that with lower recurring time, so we have a chance to see them erupt twice. And this is because they push material more aggressively and more efficiently heat that layer, essentially. So the more evolved donor stars just have these higher accretion rates, generally. This is sort of just showing the same thing, except in white dwarf mass and accretion rate space. So rather than showing in terms of the evolutionary phases, this just shows it in terms of more continuous parameters, I suppose. But I'll skip over this one in the interest of time. So I guess the final point I wanted to make in terms of these simple stellar populations and these sort of fundamental nova physics is that we can also look at, okay, how does the metallicity of your population affect its productivity in terms of novae? And what we find is that in terms of the total number of nova events, the total number of nova ejecta, and the total number of nova systems, as well as the events and ejecta per system, all of this goes down with increasing metallicity, which is to say that due to physics that I'm not going to have time to talk about here in detail, that you can ask me and I can try and put out a brief explanation at the end of the talk if you're interested. Essentially, there is like this systematic shift to lower productivities at lower metallicities, and it's significant. It's roughly a factor of 2. So this is like a normalized scale here. But that's all all the context about the fundamental physics of the nova population that you should need to understand the rest of the talk. So I'm going to move on now to what about real star-forming environments, or at least better approximations to real star-forming environments. So what about Novae and M31 in the Milky Way? So first of all, a quick word about how we actually convert between this burst of star formation to a useful galaxy, for want of a better word. So this is, for example, a burst of star formation. At time equals 0, we form our stars, and then for the next 15 years, we produce novae, right? And this is how many occur in each bin. So what we do is we take a form of this diagram, essentially, and we convolve that with an age metallicity star formation rate relation. So this is one from Kobayashi et al. 2020 that breaks down the Milky Way into the thin disk, bulge, thick disk, and halo. And what we get out of that, once we do that in that convolution, is that we get an event rate history, right, for each of the components in this case. And then we can also get distributions where we just read off at the appropriate time the distribution of, for example, the white dwarf mass, right, of all of the novae that would be observable in that time bin, right, or equivalently the event rate. So how do we do now that we've done this convolution, which, by the way, is metallicity dependent? So we account for, in principle, the metallicity evolution of our environment. We do okay. This blue bar is my hand-wavy uncertainty based on uncertainties in stellar physics and how that might affect the nova rate. But this blue line is essentially our theoretical prediction. And here we have, for the last 30 years or so, a large number of event rate estimates in the Milky Way. So there's a lot of scatter here because getting the Milky Way nova rates is not an easy observational task. But there does seem to be like, we're slightly more consistent with a certain method called the extragalactic method versus the galactic method, which just means that when you look at external galaxies and you then scale their luminosities back to the Milky Way, these are the event rates you get, versus these are ones that use actual nova data from the Milky Way in order to derive their event rate. So this looks okay. It's at the very least not orders of magnitude off, which is encouraging for population synthesis. What about M31? Well, we can do the same thing using different star formation rate histories naturally. And this is the event rate you get here. So don't worry about all the lines so much. This is about the resolution of our metallicity history. And the short answer is that it doesn't matter heaps whether we super resolve it, at least in terms of the final result. So this is the most, and this little green box here, or gray box with a green outline, is the most recent nova rate estimate for the M31. This is the second most recent, which is inconsistent. But this was kind of nice because this result came out about a week after I submitted my thesis, where we'd computed these curves a year prior or something. So it was a nice vindication, even though it was came just a little too late, but it's okay. But anyway, the point is we do pretty well for rates, but we don't do pretty well for everything. So one big discrepancy between this work and previous works is in the white dwarf mass distribution of our novae, or how we predict it should look today. So this is, for example, our theoretical prediction for the white dwarf mass distribution in the Milky Way. And this is it's not an observational distribution, but it's an observationally derived distribution by Shah et al. In 2018. Right, and these are clearly inconsistent. They were very top heavy on massive white dwarfs. And while, yes, this has a heavy element of modeling in it also, at the same time, it's like in the context of the uncertainties around what we've been assuming and everything, at the very least, we can say that the white dwarf mass distribution, as we expect it to look today, appears to be quite sensitive to the assumed physics, right? That's the minimum that we can say here, which on the one hand is very interesting and makes it a very interesting, good probe. But it's also difficult to say, okay, do we definitely get it right? Probably not. If we make different assumptions about the fundamental nova physics, probably we will arrive at quite different white dwarf mass distributions. And yeah, final word on galactic components in M31 is this is a bit of a demographic for the novae within the Milky Way. So effectively, we find that we get around 70% in the thin disk, 24% in the bulge, 5% in the thick disk, and 1% in the halo. So obviously, these numbers are quite dependent, to say the least, on our assumed galaxy model, which also has considerable uncertainties, which unfortunately remain to be looked into mostly. We can make a few comments about how different types of star-forming environments, for example, whether star formation is ongoing versus ceased in the distant past. So in essence, oxygen neon white dwarf accretors in particular, because they come from more massive stars, essentially, they're far more common in regions where star formation is ongoing. Other things, it's much weaker trends. So, but basically, if you can profile your nova population, particularly in terms of this, there is potential for being able to say, okay, to use Novae, what I mean to say is there is potential for using Novae as a probe of a star formation history. There is potential. I don't think it would be the easiest or best way to do it, but there might be something there. There might be something there. You clearly see like variation at the very least. Okay, so I've been talking a lot about novae and not a lot about abundances or chemical evolution, but for the rest of the talk, we're going to be talking about novae and their role in galactic chemical evolution, in particular lithium. So this is similar to the plot I showed before. So this is the methodology for reaching these results, essentially. So where previously I showed you an event rate delay time distribution, this is something that I call an ejector mass or an ejector delay time distribution. So the difference is, instead of tracking the number of events in each bin, now we're tracking the mass of nova ejector in each bin. And this is just colored by the donor stellar type, which isn't super important. It's just an example. Anyway, we once again need to convolve this with a galaxy model, but we also want to combine this with so isotope-specific event rate, Novae yields, essentially. So these are tables from Jordi Jose in 1998, but there are other tables which we can and do test. And the thing to know here is that not only can we do this for our nova population as a whole, for example, this ejector delay time distribution, we can also compute this for different mass brackets of novae. So what I mean by that is, suppose I've got a white dwarf of 0.6 solar masses and it undergoes a nova explosion. The nuclear synthesis from this white dwarf will be very different to one at, say, 1.2 solar masses that undergoes a nova explosion. And the great thing about these kinds of nova tables is, and I realize this is just code here, but essentially low mass down here and high mass up here, and then you've got various other physical differences. But because we have white dwarf mass specific nova yields, by breaking this down, we can map the appropriate nova subpopulation in terms of its mass to the appropriate nova yield and get a much more, in principle, realistic picture of the way that novae are behaving here. So this is like a really nice and powerful capability that Omega, so the Galactic Chemical Evolution code that we use, actually has a very nice built-in tool for. So in essence, instead of doing this manually like we did in the previous stuff for the event rates, here we use Omega to do this for us, where we input the tables and the ejector masses, and out we get is abundances for all the things. So before I show you these abundances and give you perhaps what the main takeaways for this talk will end up being, and then obviously describing and putting that in context, one final word is, so this ejector mass, right? So I mentioned that the white dwarf mass is important in terms of the nucleosynthetic rates, obviously, but it's also important in terms of how much ejector mass each sort of subpopulation puts out, right? And there are distinct differences. So between that. So to look on the left-hand panels here, what we have here is the mass ejected per hydrogen nova eruption. And then on the top panels, the events, and then the bottom panels, the ejector mass. So what this figure is illustrating is, or showing, is that suppose we've got relatively massive white dwarfs. So remember, these are the oxygen neons. These have far lower mass ejected per hydrogen nova. So this is a direct result of them having lower critical ignition masses as these two things scale, right? So when we're looking at nova event rates, massive white dwarfs do very well for themselves because they have, as I was saying, very low critical ignition masses. So per unit accreted material, they produce a lot of novae. But because the ejector mass scales with the critical ignition mass, this advantage disappears when you start looking at nova ejector, right? Which is obviously what you care about in terms of nucleosynthesis. So this is the distribution of the ejector mass between the different white dwarf mass regimes. So as you can see, where massive white dwarfs were doing very well for themselves in terms of events, they actually compute almost negligibly in terms of the total ejector mass of white dwarfs, right? So the net effect of all this is that low mass white dwarfs completely dominate when you consider the mass ejection profile of novae in terms of the white dwarf mass. So who cares about massive white dwarfs, right? It's clearly all the carbon oxygen white dwarfs that are doing all the heavy lifting. Well, it's not quite so simple. For relatively low mass number abundances, that is more or less true. So what this plot shows is for a set of isotopes between helium-3 and neon-22. What we see here is that for the light stuff, so low mass white dwarfs are sort of more purpley, high mass white dwarfs are yellow, and then each of these different bars is a different nucleosynthetic yield table. So by Jordi 98, Starfield 2009/2020. So this is a combined of Starfield's two papers, and then another one by Jordi Jose in 2020. But the point is that you can see very clearly that, yeah, in most cases, the lower mass white dwarfs, so sort of everything up to very light green, They do. They completely dominate the total mass of each isotope produced, right? You see this for almost all of them. When we get to when we start getting to the heavier stuff, say neon 20, neon 21, neon 22, you do see a little bit of a resurgence at the high mass end. So this is because as you reach higher and higher, you need more and more massive white dwarfs and more extreme and hotter burning conditions in order to sort of spill that reaction rate into the higher mass number isotopes, right? And if we consider the other half of the Nova network that we were considering, you can see that this becomes even more prominent to the point where the most massive white dwarfs for elements like sodium-23, sulfur-24, sulfur again, like the more massive you get, the more the higher mass white dwarfs matter in essence, despite the fact that they were so underrepresented in the total ejector mass, right? This is how strongly dependent on the white dwarf mass these Novae yields are. But all of this is comparing Novae to Novae, right? What about compared with other stellar sources? How do Novae do then? The answer is pretty badly, basically. For almost all isotopes, Novae can contribute negligibly with only a few exceptions. Those being carbon-13, where Novae, comparing, so by the time we reach the time that the sun was formed, essentially Novae produce roughly between 10 and 36%, where this uncertainty is due to the different theoretical yield tables we're using of carbon-13. So that's significant, but not dominant. Nitrogen-15 between 21% and 36%, again, significant, but not dominant. And oxygen-17 between 8 and 13%. But of other isotopes, only very trace amounts, oxygen-16, helium-3, and even less of the more massive stuff, right? So compared with AGB stars, type 1a supernovae, massive stars, they just don't produce a lot, right? It's their contributions are small. So in many ways, the assumptions to ignore them that have been made for many, many years have, at least for most isotopes, borne out here. But the other element that I haven't really included in this plot is lithium. So lithium is particularly interesting because of something called, well, something that I'll call here, because there's many lithium problems, the galactic solar lithium problem. So the short version of this problem is that when we look at the abundance of lithium in pre-solar grains, we can calculate a lithium abundance. And in essence, it's high. It's too high compared with how much lithium and how difficult lithium is to make, according to our current theoretical knowledge. We cannot make enough lithium to explain the amount of lithium we find in meteorites around the sun. So this is called the solar lithium problem, or the galactic solar lithium problem, right? And it's been around for a long time, and Novae have been proposed as a potential solution to this for a long time. But generally, it hasn't worked super well. So in essence, in our modeling, we took into account, obviously, our galactic model, but also not only the theoretical yields from Jordi Jose, this is Recurrence 2017, and then Sumner Starfield and so on. All of these, the point is that all of these solid lines are theoretical, and they all basically fall on top of each other down here, right? They don't really do any better than any of the previous works in terms of explaining this. And in fact, in some ways, they do worse. But when we take into account recent observations of lithium in actual nova ejector, right? So this is, and the next slide I'll show will be what level these are actually at, right? Which are much higher than the theoretical predictions. What we find, and this sort of just falls out, is that combining our theoretical models for novae and the ejector mass and a reasonable model for the galaxy in terms of most other isotopes and abundances produced by Omega, it basically passes right through the solar point in essence, right? So it just kind of works. So in essence, based almost entirely off this diagram, we can say that, all right, lithium novae appear to be viable. And in terms of how certain that is, in terms of physical uncertainty, the conclusion that we draw is that it's actually fairly robust, certainly to binary uncertainty. We varied the binary assumptions we made by, well, actually an unreasonable amount. And this budges noticeably, but not that noticeably, certainly not within the shaded region here. So what is this shaded region here then? Because this is a rather large variation. This shaded region is 1 sigma uncertainty on our observations of lithium ejecta in novae. So in other words, from this diagram, we can also say that, at least according to our current understanding of where we're at, and this is at this point an isolated study, so certainly future work is needed, but observational uncertainty appears to dominate over theoretical uncertainty in this case, at least, which is always a useful thing to know. So further observations of lithium abundances in nova ejecta, I would say, are extremely well motivated. So about those lithium abundances, this is, at least at the time that I did the work, there may have been another couple released, but this is all of the novae where we have lithium-7 abundances. So yes, it says beryllium-7 here. This is because beryllium-7 is actually what you form during the nova nucleosynthesis, nova ejecta, and then that decays into lithium-7. So it's got a relatively rapid half-life. So it's a good proxy. But in essence, the way we apply this is that if you recall, when I was talking about mapping the appropriate nova white dwarf masses into the appropriate nova ejecta, so because we don't actually know the white dwarf masses for almost any of these novae, in fact, none of them, we can't actually do that trick here. So instead, what we do is we just take them all, take an average, and compute the standard variation and treat that as the uncertainty. There is an additional, can I go back? Nope. Oh, yes, I can. So there is an additional uncertain assumption in terms of the mixing parameter that sort of is needed to convert this into a max fraction, and basically it tells you how much hydrogen is left over in your nova ejecta. So this is why we have a gray and a blue, but they're almost just indistinguishable here. So the point is that it doesn't really matter. But the point is that this is another important difference between these observations, these theoretical models. So where previously we could assign the appropriate mass brackets, we can't actually do that here. So basically any studies that look at, for example, or did a like dedicated studies looking for the white dwarf masses of these novae would also be a highly valuable and well-motivated way to move this forward, I guess, in terms of improving the certainty on this result. For the reason that instead of basically applying this to all of our novae, then we would have the ability to, again, map the appropriate masses and get a better idea. Having said that, preliminary testing indicates that it probably wouldn't change this fundamental result, that essentially when you use the observed lithium abundances in nova ejecta, which are roughly an order of magnitude or two higher than those theoretically predicted, it does very well in terms of comparing with that solar lithium abundance and also that upper envelope of, for example, the Galar data. Right, and you do expect it to match not the bulk but the upper envelope here, in that lithium destruction in the envelope of stars is a well-known and expected phenomena. And that's actually the end of the talk, essentially. So in terms of the conclusions and summary, so I talked about how common envelope physics we expect to be particularly important to the nova systems which produce the most novae, so the most efficiently producing systems in terms of the event rate. Metallicity dependent stellar evolution reduces nova rates as metallicity increases. So in the past, when metals were poor, our per unit star formation, we got more novae essentially. Nova rates in M31 and the Milky Way we find to be relatively consistent with observations in terms of our predictions. So our models at least appear superficially reasonable in that sense, in terms of that sanity check. But conversely, the white dwarf mass distributions we find to be inconsistent with previous works, indicating essentially that the white dwarf mass distribution seems to be quite sensitive to the assumed physics. And then in terms of galactic chemical evolution, we find that novae from high mass white dwarfs, despite having far less ejecta, can still contribute, at least significantly in the context of novae, for the high mass number isotopes, but much less for the lower mass isotopes, such as lithium, carbon, and so on. And then, yeah, these were the isotopes where we found novae did matter, even in the context of all the stellar sources. So AGB stars, massive stars, and type 1a supernovae. We found that they did contribute noticeably to these isotopes, but not others. And then, yeah, finally, as I said, using the observed lithium data, we found that novae appear extremely promising candidates for resolving the galactic solar lithium problem. Using theoretical data, we found that no, they don't work. In fact, they don't lift the curve noticeably at all from the case where novae are completely ignored. So it very much does hinge on those the validity of those abundances, observed lithium abundances. So were those to, for example, be revised for whatever reason, then novae would no longer appear promising. But yeah, thank you for your time, and that's the end of the talk.